Now, where I want to spend a little bit more time is on visualization of modulation schemes. And the reason for that is because once you learn how to visualize a modulation scheme, you can actually use that to make decisions of how are going to design your system. So let me give you a simple example. The whole idea behind visualizing a modulation scheme is actually coming from the fact that we're only using sine and cosines. These are, again, orthogonal signals. And in a binary phase shift keying, for example, approach, which is almost the same as an ASK with two different amplitudes, you can basically encode the signal in the phase. So you can have either a phase of 0 or a phase of pi. And essentially, you end up with either a number times a cosine or minus that number times a cosine. And that number here, I'm actually including some useful information. This is the energy of the signal, or the energy of the bit. And this is the period of the signal. So if you actually were to plot this on an axis, you could basically say that I'm basically transmitting a signal that has an amplitude either plus square root of EB or minus square root of EB. And that's basically it. Now, the reason that this becomes quite useful is essentially now we are saying we have a basis function, which is my cosine, and we can expand all the signals of that modulation scheme along this basis function. In more complex cases, we need the sine as well to expand the signal, not just the cosine. But in the single BPSK modulation scheme, that is actually sufficient. Let me show you an example of an 8 PSK, in which case we don't just change the phase by in a binary way, but we rather use 8 different phases to encode information. Now we're going to have basically a variety of cosine and sine possibilities. This I-axis is the in-phase axis called cosine. This is the quadrature axis called sine. And in an 8 PSK modulation scheme, you basically have 8 different possibilities that I'm showing here with the 8 circles, 8 red circles. And each one of those circles can actually represent a symbol. And because we're using 8 different phases, we can encode log 8 or 3 bits in each symbol. So in reality, what's happening is that the receiver knows that it's going to receive one of those 8 symbols that you see here. And all that the receiver has to do is decide which of those symbols did they actually get. And so, for example, it will, because of noise, interference, and corruption, and all of the other things, it will get a signal somewhere here. And it will say, OK, if this is the signal that I received with this much magnitude on cosine and sine, what's the most likely symbol that the receiver, that the transmitter actually sent me? If you were to make a logical decision, you will say probably they sent me this one. But honestly, if the noise was too high, it's possible that that signal might have been this guy, or even worse, maybe that signal may have been this one. Depends on how bad the channel was. The reality, however, is that in most well-designed systems, the most likely error that you might make is between neighboring signals, because that distance is the smallest. And so the first way I want to train your eyes to see is that when we design a signal constellation diagram like the one that you see here, the distance between 2 neighboring symbols is actually key for removing errors. The larger you make actually that distance, the less likely it is that you're going to have an error. And that's the value of this type of a graphic representation, is the minute you actually see one of those diagrams, you can make a decision immediately of what's the tolerance of that system to noise. Similarly, you can actually make a decision of whether a modulation scheme is better than another. For example, if I were to compare this diagram with a single BPSK, in BPSK, remember, I have only 2 symbols right here, you can immediately tell me that 8 PSK, yes, it transmits 3 bits per symbol versus BPSK that transmits only 1, but it's far more likely to make an error because the distance between 2 neighbor symbols in the 8 PSK is much smaller than the distance between 2 neighbor symbols in BPSK. And that's why you will see standards when there is a high noise, they will actually reduce the data rates because they will shift to a simpler modulation scheme, as I just described before. The last thing I want to mention about this diagram here is this thing called gray code. You may have heard of gray code before, and we're not going to spend time in this course, but just so you know what it is, it's basically a way to assign bits to symbols. For example, you can see here that I have assigned the bits 0, 1, 1 to the symbol here, and this 0, 0, 1 to this symbol. That's not random. If you actually look closely, these two arrangements differ by only 1 bit. There is only 1 bit difference between any two neighboring symbols, not just between those two. And that's key. The reason for that is because if I make an error, as I mentioned before, it's far more likely I will make the error between two neighboring symbols. So I make one symbol error. If I follow the gray code I have here, that translates to 1 bit error. At the end of the day, I care not about symbol errors, but bit errors. If I had done a bad scheme, I could have done as bad as 1 symbol error leading to 3 bit errors. How could I have done something so horrendous? By assigning here 1, 1, 1 and here 0, 0, 0. That would have been pretty bad. That's one reason why you can lose your job, right? So, so keep that in mind, that when we encode bits to codes, the second thing that the signal constellation diagram tells us is how that should happen. You can see here that the difference between 0, 0, 0 and 1, 1, 1 is actually really high, as it should be. All right, let me give you an example of the QPSK signal constellation diagram. And as I mentioned before, we are going to receive something in real life that will be not really on top of any of the ideal symbols, and then we're going to have to make a decision. So usually, by the minute you see a signal constellation diagram, you can decide on decision boundaries, which, given that everything is equal probability, you're likely going to put them at the center, in the middle, as I have done here. And we show you a few other images. This is a signal constellation diagram from another scheme called quadrature amplitude modulation, or 16 QAM in this case, where I'm basically transmitting 4 bits per symbol. So now clearly I need 16 different symbols, and I basically arrange them in that square. Again, if you check the distances, the shortest distances basically try to differ by as few bits as possible. And you can clearly see that the bits that are differ by a lot are quite far away. This is a few other signal constellations you will see out there. And again, once you see enough of them, now you can start understanding, for example, why a system might actually go from a 64 QAM to a 16 QAM if the noise increases. It's because in the same space, I will put basically fewer symbols. Now, besides all of this qualitative discussion, there is something called error vector magnitude, which is basically a quantitative measure of how well you're doing. So error vector magnitude is actually defined by this equation here. And the third reason why signal constellation is so useful is because you can actually compute it practically by simply knowing the signal constellation diagram. So let me show you what I mean. Here I have zoomed in. This is the symbol that I'm expecting to receive. Let's say the desired symbol. And all the green dots is what I'm actually getting. So there's going to be a geometrical distance between the green dot here and the symbol that I want in transmission number 1. There's going to be a different geometrical distance in transmission number 2 or in transmission number k. So I can do a bunch of these transmissions, and then I can basically sum up all of these distances. Of course, the less the sum is, the better. I can divide this by how much power I'm transmitting, which is this main distance from the center. It's related to this main distance. And then I can compute my error vector magnitude. Obviously, the smaller this number is, the better I'm doing. And so this is one quantitative measure that will allow you to compare two systems or two modulation schemes.